At night, the world looks like a net of light. Cities glow with an astonishing brilliance, streets and buildings etched against the dark. Hospitals shine as beacons of care, advanced instruments humming through the quiet hours. Across the vast oceans, powerful ships sail on missions that last for months, moving with a silent, steady strength. Far out in the cold emptiness of space, robotic spacecraft carry tiny, warm hearts, small heat sources keeping them alive far from the sun. Many of these lights, these machines, these explorers use a strange and powerful gift from science. They draw their energy from deep inside the heart of the atom. How did we first learn that ordinary matter hides such immense and potent energy? The journey to this knowledge was not a straight path. It began with small, puzzling curiosities and grew to massive, complex machines. This journey gave us a new source of power and changed how we see the world and our place within it. In the late 1800s, the picture of the universe seemed simple and settled. Most scientists believed atoms were the tiniest building blocks of everything. They were imagined as small, hard, perfectly solid spheres, microscopic billiard balls. Atoms were thought unchangeable and eternal. You could combine them into molecules, but you could never split an atom itself. That idea felt safe, orderly, and complete. It provided a satisfying foundation for chemistry. Then a surprise discovery in a quiet laboratory began to unravel it all, setting science on a dramatic new course. A profound question emerged. If atoms were not indivisible, what were they made of? And if they could change, what did that change produce? In 1896, Henri Becquerel studied minerals that glowed after sunlight. He placed uranium salts near photographic plates wrapped in black paper. To his surprise, the plates became darkened, as if exposed to light. But light had not caused this change. Something invisible and powerful was emanating from the rocks. Becquerel had found a new kind of ray, radioactivity. What was this mysterious energy coming from seemingly inert matter? Before the turn of the 20th century, the scientific consensus was firm and comforting. The universe was built from atoms, a concept inherited from the ancient Greeks, but now supported by a wealth of chemical evidence. These atoms were thought to be the smallest possible pieces of a chemical element. An atom of gold was the smallest bit of gold you could have. It was indivisible, a solid and permanent particle. This model, often attributed to John Dalton, had served science wonderfully. It explained how elements combined in fixed ratios to form compounds and provided a clear mechanical picture of the material world. There was no hint of any deeper, more volatile power locked within. This view of the atom as a simple, solid sphere was not just a lazy assumption. It was the best explanation for the available data. Chemists could weigh elements, mix them, and predict the outcomes of reactions with astonishing precision, all based on the idea of indestructible atoms rearranging themselves. The world of physics, meanwhile, was focused on grander things like light, electricity, magnetism. The atom was the chemist's domain, a reliable and rather boring little particle that did its job without any fuss. The idea that this tiny, stable entity could harbor a source of colossal energy was not just unknown, it would have been considered absurd, a violation of the established laws of nature. The scientists of the late 19th century felt they were nearing the end of physics. Some prominent figures declared that all the fundamental laws had been discovered, and all that remained was to refine measurements to a greater degree of accuracy. The universe, they believed, operated like a vast, predictable clockwork mechanism. Energy was energy, and mass was mass. The two were entirely separate categories of existence. The law of conservation of energy stated that energy could not be created or destroyed, only changed in form. The law of conservation of mass said the same for matter. These were bedrock principles. No one suspected they were about to be shaken to their core. This stable, predictable world began to crumble with a series of unexpected discoveries. First came the electron in 1897, a particle much smaller than an atom, proving that atoms must have internal parts. Then came Becquerel's discovery of radioactivity a year earlier, a phenomenon that seemed to defy the conservation of energy. These strange rays emanated from uranium without any apparent power source, continuing day after day, week after week. It was as if a lump of coal were burning without consuming any fuel or needing any air. Where was this mysterious and seemingly endless energy coming from, if not from the atom itself? The story of nuclear energy truly begins in a darkened room in Paris in 1896. The scientist Henri Becquerel was pursuing a fashionable line of research, phosphorescence, the ability to glow after exposure to sunlight. He wondered if these glowing minerals emitted the newly discovered X-rays. His method was simple. He would place a uranium salt on a photographic plate. He wrapped the plate in thick black paper. He exposed the setup to the sun. Then he developed the plate. The plate showed a silhouette of the mineral. One week, the Paris sky was overcast. He put the wrapped plate away in a dark drawer. He put the uranium salt away in the drawer. Several days passed. He decided to develop the plate anyway, expecting a faint image. Instead, the image was stunningly clear and intense. The sun had played no part. The uranium salt emitted powerful, invisible rays on its own. A complete accident, a ghost in the machine. The discovery sent a shockwave through science. It was named radioactivity, challenging known physics. Where was the energy coming from? A log burns and turns to ash. A battery powers a circuit, then runs down. Becquerel's uranium poured out energy without obvious change. A profound puzzle. The source had to be inside the uranium atoms themselves. Inspired by Becquerel, Marie Curie, working, and Pierre Curie, working, they began a systematic search for other radioactive substances. In a drafty shed laboratory, using a sensitive electrometer designed by Pierre, they tested every element they could find. They discovered pitchblende was far more radioactive than pure uranium. It suggested a new, undiscovered, powerful element. What was this mysterious substance, and could they isolate it from tons of raw ore? They obtained tons of pitchblende waste from a mining company and began the grueling process of chemical separation. It was physically demanding and dangerous work performed with rudimentary equipment in a leaky storeroom. Over 4 years, Marie Curie stirred boiling cauldrons of black, sticky ore, painstakingly isolating fractions that showed higher and higher levels of radioactivity. Their relentless effort paid off. In 1898, they announced the discovery of not one, but 2 new elements. Polonium, named after Marie's native Poland. Radium, named for its intense radioactivity. Radium was millions of times more radioactive than uranium, glowing faintly in the dark with an eerie blue light. The Curie's work proved radioactivity wasn't just a quirk of a few odd materials, but a fundamental characteristic of certain elements. The energy was clearly coming from within the atom. This meant the atom was not the simple, solid ball everyone had imagined. It had to have a complex inner structure capable of powerful transformations. Atoms were not fixed and eternal. They could decay, changing from one element into another while releasing a torrent of energy. The old model of the atom was shattered. But if the atom wasn't a solid sphere, what did it actually look like inside? The next piece of the puzzle came from a brilliant New Zealander named Ernest Rutherford. Working in Manchester, England, he designed a clever experiment to probe the atom's structure. He fired a stream of tiny, positively charged particles, called alpha particles, at an incredibly thin sheet of gold foil. He expected the particles to pass straight through, like bullets through a piece of tissue paper, with perhaps some minor deflections. Most of them did. But to his utter astonishment, a tiny fraction, about 1 in 8,000, bounced back as if they had hit something solid and massive. Rutherford later described his surprise. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. This result could only mean one thing. The atom was not a uniform pudding of matter. Instead, it must be mostly empty space. All of its positive charge and almost all of its mass had to be concentrated in an incredibly small, dense center. Rutherford called this center the nucleus. The tiny, negatively charged electrons must be orbiting this nucleus from a great distance. How could such a tiny nucleus contain so much mass and, as radioactivity suggested, so much energy? While experimentalists were taking the atom apart piece by piece, a young patent clerk in Bern, Switzerland, was rethinking the very nature of reality. In 1905, Albert Einstein published several revolutionary papers. One of them contained an idea of startling simplicity and immense consequence. It proposed a deep and fundamental connection between mass and energy. Before Einstein, these were considered two entirely separate things. Mass was the stuff of an object, while energy was what made it move or get hot. Einstein argued that they were, in fact, two different facets of the same underlying reality. Mass, he proposed, was a form of concentrated, stored-up energy. He expressed this relationship in what would become the most famous equation in science: E equals mc². In this equation, E stands for energy, m for mass, c for the speed of light. The speed of light is a huge number, about 300,000 kilometers per second, and squaring it makes it astronomically larger. What the equation reveals is that a minuscule amount of mass can be converted into a tremendous amount of energy. It's not that mass is turned into energy, it's that mass is energy. The equation is like a conversion rate, telling you how much energy is locked up within a given amount of mass, just as a currency exchange rate tells you how many dollars are in a pound. At the time, this was a purely theoretical idea. Einstein's equation was a profound insight into the workings of the universe, but there was no known way to prove it experimentally. It seemed like a cosmic secret with no key. The energy released by chemical reactions, like burning wood, was far too small. The mass lost was infinitesimal and impossible to measure. The energy from radioactivity, however, was much greater. Scientists began to suspect that the energy of radium, uranium, came from this very process. As these atoms decayed, they must be losing a tiny, tiny fraction of their mass, which was being converted into the energy of the emitted rays. This idea provided a stunning explanation for the sun's power. For decades, astronomers had been baffled by what could keep the sun burning for billions of years. Chemical burning would last only a few thousand years. Einstein's equation provided the answer. The sun was a gigantic nuclear furnace, converting its own mass into the light and heat that bathe our planet. But even with this cosmic proof, the question remained for people on Earth. Could this immense atomic energy ever be unlocked and controlled by humans? Or would it forever remain the exclusive domain of the stars and a few strange, glowing rocks? The quest to unlock the atom's energy took a dramatic turn in the 1930s. Scientists had discovered a new particle, the neutron, in 1932. Because it had no electric charge, the neutron was the perfect tool for exploring the nucleus. Unlike positively charged alpha particles, it wasn't repelled by the positive charge of the nucleus and could slip right in. Across Europe, physicists began bombarding every element they could find with these new projectiles. In Rome, Enrico Fermi's group found that bombarding uranium with neutrons produced strange, new radioactive substances. They believed they had created new, heavier elements beyond uranium, but the results were confusing and hard to interpret. The mystery was finally solved, again partly by accident, in Berlin in late 1938. Otto Hahn, Fritz Strassmann. They were meticulously repeating Fermi's experiments. They bombarded uranium with slow-moving neutrons, hoping to confirm the creation of heavier elements. Instead, their chemical analysis kept finding something utterly unexpected: traces of barium. Barium is a much lighter element, with a nucleus roughly half the size of uranium's. It was like firing a pebble at a window and finding a cannonball among the shards. Hahn was baffled. As a chemist, he was certain of his results, but as a physicist, he knew it made no sense. He wrote to his former colleague, Lise Meitner. She received Hahn's letter while visiting her nephew, Otto Frisch. As they discussed the bizarre finding during a walk in the snow, a picture began to form. They recalled the model of the nucleus as a wobbly, liquid drop. Perhaps the incoming neutron had made the large uranium nucleus so unstable that it had oscillated violently and split in two, like a water droplet breaking apart. They sat down on a log and began to calculate the energies involved. They quickly realized the implications. The two smaller nuclei that were formed, when added together, had slightly less mass than the original uranium nucleus. A tiny amount of mass had disappeared in the process. Using Einstein's E equals mc², Meitner and Frisch calculated the energy that this lost mass would release. The number was enormous, far greater than any known chemical reaction. They had discovered the mechanism. The nucleus had been split. Frisch coined the term fission to describe this process, borrowing the term from cell division in biology. The door to the atom's energy store had been kicked open. But could this single event lead to something more? The discovery of fission was momentous, but the true key to unlocking its power lay in a secondary detail of the process. When Lise Meitner and Otto Frisch calculated the energy release, scientists realized splitting a uranium nucleus made two smaller nuclei and released a burst of energy. It also ejected neutrons. This was the critical insight. Those freed neutrons could fly off and strike nearby uranium nuclei, causing them to split as well. Each fission released more neutrons, which could trigger even more fissions. This created a cascade, a rapidly multiplying series of events. It was a chain reaction, a room filled with thousands of set mousetraps, each holding two ping-pong balls. If you drop a single ball into the room, it might set off one trap. That trap flings its two balls into the air. Those two balls set off two more traps. Those two traps fling four balls. Four balls set off four more traps. In a fraction of a second, the room erupts in a storm of flying ping-pong balls. One small event could trigger an exponentially growing, self-sustaining reaction that would release a colossal amount of energy very, very quickly. Physicists immediately understood that controlling this chain reaction was the central challenge. To create a sustained reaction, you needed a sufficient amount of fissionable material packed together. This is called the critical mass. If the lump of uranium is too small, too many neutrons will escape from its surface before they can hit another nucleus, and the chain reaction will fizzle out. If the mass is large enough, or critical, then enough neutrons will be captured to keep the reaction going at a steady rate. If the mass is supercritical, the reaction will grow exponentially, leading to an explosion. Engineers also realized they needed ways to manage the speed of the reaction. They needed a brake and an accelerator. This led to the concept of moderators and control rods. It turns out that uranium-235, the fissile isotope, is much more likely to split when hit by slow-moving neutrons. A moderator is a substance, like graphite. A moderator is a substance, like heavy water, mixed in with the fuel to slow down the fast neutrons released by fission, making them more effective at causing the next round of fission. Control rods are made of materials like cadmium that are excellent at absorbing neutrons. By inserting the control rods into the fuel, you soak up neutrons and slow the reaction down. Pulling them out speeds it up. The first attempt to build a machine that could harness a controlled nuclear chain reaction took place under the most unlikely of circumstances. It was not in a gleaming modern laboratory, but in a squash court beneath the abandoned football stands of the University of Chicago. The year was December 2nd, 1942, and the world was at war. A team of scientists, led by the brilliant Italian physicist Enrico Fermi, worked in secrecy as part of the Manhattan Project. Their goal was to prove, once and for all, that a self-sustaining chain reaction was possible. They called their experimental device Chicago Pile 1, or CP1. The pile was a monumental but crude construction. It was a carefully stacked lattice of 45,000 graphite blocks. The graphite acted as the moderator. Embedded within this black, dusty mountain were 6 tons of pure uranium metal, 50 tons of uranium oxide. The entire structure was built by hand, layer by layer, by physicists, and even some local high school students hired for the job. There was no radiation shielding and no cooling system. The team believed the power level would be too low to be dangerous. As a primitive safety measure, a man stood by with an axe, ready to cut a rope that would drop a control rod into the pile in an emergency. On the cold morning of December 2nd, 1942, the final test began. The small group of scientists gathered on a balcony overlooking the pile. The air was thick with tension and the fine graphite dust. Fermi calmly directed the proceedings, ordering the cadmium-plated control rods to be withdrawn from the pile one by one, inch by inch. Neutron detectors, which made clicking sounds, were the only audio indication of what was happening inside the silent black pile. As the last control rod was slowly pulled out, the clicking from the counters grew faster and faster, eventually merging into a steady hum. The instruments showed the reaction was self-sustaining. For 28 minutes, the pile operated, producing a tiny amount of power, about half a watt, just enough to light a small flashlight bulb. But the amount of power was irrelevant. Fermi's team had done it. They had initiated and controlled the first artificial nuclear chain reaction. They had lit the first fire of the atomic age. After confirming the results, Fermi ordered the control rods reinserted and the reaction stopped. The experiment was a resounding success, a quiet, intellectual triumph that would change the course of history. How could this small, controlled flicker of atomic energy be scaled up to generate useful power? Now, from heat to light. The success of Chicago Pile 1 proved that a controlled chain reaction could produce heat. The next great engineering challenge was to convert that heat into a useful form of energy, like electricity. The solution, in principle, was surprisingly conventional. It drew upon technology already over a century old. The core idea is the same one used in a coal or natural gas power plant. Use heat to boil water. Use the resulting steam to spin a turbine. Use the turbine to drive an electric generator. The nuclear reactor is simply a new and incredibly powerful kind of furnace. Here is how a typical modern nuclear power plant works. Inside the reactor core, the controlled fission chain reaction generates an immense amount of heat. This heat is absorbed by a coolant, usually water, pumped through the core. In a pressurized water reactor, that water is kept under extremely high pressure to prevent boiling, reaching over 300 degrees Celsius. This superheated water flows through a heat exchanger, essentially a giant radiator. The reactor's hot water flows through pipes immersed in a separate secondary loop of water. The heat is transferred, and the secondary water flashes into high-pressure steam. The high-pressure steam is channeled through pipes to a massive turbine. The turbine has dozens of fan-like blades attached to a central shaft. The steam jet expands against the blades and spins the turbine at thousands of RPM. That spinning shaft is connected directly to a generator. Inside the generator, giant magnets spin within massive coils of copper wire. Michael Faraday discovered electromagnetic induction in 1831. Moving a magnet near a coil of wire creates an electric current. The reactor provides heat. The water and steam provide the mechanical link. The turbine provides the motion. Faraday's law turns that motion into the flow of electrons we call electricity. The steam, having done its work, is cooled and condenses back into water. The condensed water is pumped back to the heat exchanger to begin the cycle anew. From a split atom to a lit city, heat, steam, motion, and magnetism. The atom offers a double-edged gift. Once the principle of controlled fission was established, its application spread far beyond electricity for public grids. The extraordinary energy density of nuclear fuel, A small amount of uranium can produce as much energy as millions of times its weight in coal oil, made it ideal for specialized situations where size-weight refueling opportunities are critical constraints. One of the first and most transformative uses was naval propulsion. Nuclear-powered submarines using compact reactors could operate for months or years without needing to surface to refuel, giving them unprecedented range and stealth. In medicine, nuclear science opened new windows into the human body and provided new tools for fighting disease. Doctors use radioactive isotopes as tracers, created in research reactors. Injected into a patient, these tracers travel to specific organs and emit faint radiation detectable by special cameras, creating images that reveal organ function. This field, known as nuclear medicine, is essential for diagnosing many conditions. Highly focused beams of radiation are used in radiotherapy to target and destroy cancerous tumors with precision, saving countless lives. Nuclear technology has also enabled deep space exploration. For missions far from the sun, where solar panels fail, radioisotope thermoelectric generators, RTGs, provide steady power. These are not reactors. They use heat from the natural radioactive decay of plutonium to generate electricity. RTGs powered probes like Voyager. Voyager still sends data beyond our solar system after 4 decades, and the Curiosity rover on Mars. We must also acknowledge the shadow of this science. The same physics that can light a city can create weapons of unparalleled destruction. The first uncontrolled chain reaction-powered atomic bombs developed during the Manhattan Project. This history is inseparable from the atomic story and has shaped global politics, public perception, and stringent international regulations governing nuclear materials. We state this plainly and soberly, a stark reminder that scientific knowledge brings immense responsibility. Today, as the world confronts the urgent challenge of climate change, nuclear power is being re-examined for its potential role in a low-carbon energy future. Traditional large-scale reactors continue to provide a significant amount of carbon-free electricity around the globe. However, the future of nuclear energy may look very different. Engineers and scientists are actively developing a new suite of technologies designed to be safer, more efficient, more versatile. These are often grouped under the name Generation 4 reactors. They incorporate revolutionary new designs, fuels, cooling systems. Among the most promising new concepts are small modular reactors, or SMRs. Unlike the giant custom-built plants of the past, SMRs are designed to be smaller, simpler, manufactured in a factory setting, which could make them cheaper and faster to build. Their smaller size would allow them to be deployed in a wider variety of locations, such as powering a remote town, an industrial complex, a large data center. Many of these advanced designs also incorporate passive safety features. They rely on the fundamental laws of physics, gravity, natural convection to shut down and cool the reactor in an emergency without needing human intervention or external power. Of course, significant challenges remain. The issue of nuclear waste is a primary concern. The spent fuel from today's reactors remains radioactive for thousands of years and requires secure, long-term storage. While deep geological repositories are considered the safest permanent solution, their political and social acceptance has been difficult to achieve. Some advanced reactor designs could help with this problem by being able to burn existing waste as fuel, reducing its volume and long-term radioactivity. The science is complex, but the goal is to create a more sustainable nuclear fuel cycle. Safety is, and always will be, the paramount consideration. Public trust in nuclear technology is fragile, shaped by the memory of accidents like Chernobyl, Fukushima. The future of nuclear power depends not just on superior engineering, but also on a culture of unwavering commitment to safety, transparency, continuous learning. Building this trust requires open communication, independent regulation, demonstrating that the lessons of the past have led to verifiably safer systems. The path forward will require a careful balancing of technological innovation with social and political realities. The story of our relationship with the atom is a journey. It began with a simple, puzzling observation, a strange fogging on a photographic plate. It grew through the patient work of curious minds in dusty laboratories and the bold, imaginative leaps of theoretical physicists. It culminated in the quiet, tense success in a Chicago squash court, where humanity first controlled the fire hidden within matter. From there, it branched out, transforming our world by lighting our cities, healing our sick, and carrying our robotic emissaries to the farthest reaches of the solar system. This journey has shown us that the universe is a far more wondrous and powerful place than we had ever imagined. The discovery that mass itself is a condensed form of energy, unlocked through the splitting of the nucleus, represents one of the most profound shifts in human understanding. It has connected the quiet truth of Einstein's E equals mc² to the humming turbines of a power plant and the diagnostic tools of a modern hospital. It has given us a tool of immense power, capable of both remarkable creation and terrible destruction, forcing us to confront the deepest questions of our own wisdom and responsibility. We now stand in a world illuminated by the glow of our technologies, a world shaped by the knowledge we have gained. We can see the tangible results of this long and complex story every day. The atom still holds its great power, and we now know many of the secrets to unlocking it. We have learned much about how to use it safely and productively. We also know the high cost of carelessness and the supreme value of caution and restraint. The scientific voyage is not over. New questions, new challenges, and new possibilities continue to emerge from our ongoing exploration of the atom's core. The hidden fire that Becquerel first glimpsed over a century ago now invites us to make our wisest choices. The knowledge is in our hands, but the path we take is not predetermined. It will be forged by our ingenuity, our prudence, and our shared vision for the future. The story is not finished. It continues to be written by the decisions we make today. As we look toward a future that demands both more energy and a healthier planet, we are left with a clear and vital question. How will we choose to use this powerful atomic gift?